Yeah, good afternoon. It's Charlie ZL2CTM. Well, just got back off another week away and have just got back into playing around with a 20 metre portable rig that I'm looking at building up. And what I was playing around with is the design of the RF power amplifier driver circuit. So this is going to be a small amplifier here, which ideally I want to be able to generate half a watt into a 50 ohm load, which in the actual radio itself will be an RF 510 power amplifier, single-ended, nice and simple to generate that sort of around 5 watts. So that's the plan. So in terms of the driver itself, looking at a two-stage driver, we'll look at the circuit very shortly. Trying to keep things really simple, just using really available parts. In this particular case, the 2N3053. I acknowledge they're not the perfect part for that, which we'll see in a sec, but the cheap, plentiful, and certainly easy to get hold of around here. So this video here, I just want to make it very clear up front that this is not a tutorial. I am not an expert in any way, shape or form in any of this. This is very much a video log of what I did in terms of the calculations and then wiring it up and then doing the testing. So it's a log, not a tutorial. Right, so in terms of the circuit itself, just keeping things nice and simple. It's a two-stage amplifier. Like I say, built around two N3053s. Wanted to generate as an output around half a watt. Looking at somewhere between 20 and 30 dB. With, say, roughly from a design point of view, 20 dB on the first stage, or what I'm calling stage 1, and then 10 dB on stage 2. Using those FT30 sets again, 3053s. So from the spec sheet, they have a transition frequency of 100 megahertz, which is not ideal for 14 megahertz or the frequency of operation. As a rule of thumb, that FT should be 10 times my operating frequency. So like I say, not ideal for 14 megahertz, but hey, I'm going to give it a go and see how she works out. The HFE off the spec sheet for the kind of currents I'm looking at ranges between 50 and 250. So as you'll see later on, we'll use the geometric mean for determining the DC biasing for those two devices. From a power dissipation point of view, they're rated for 5 watts. So we'll need probably not so much a heatsink on the first one with the current we're looking at, but certainly on the second one, as you'll see later on, it gets a little bit warm, but certainly I've had it running for minutes and minutes on end, and it's certainly not a problem at all. I've got here portable from a design point of view, and why I mention that is while I need to have the right amount of power going into these devices to generate the kind of power I need, I want to try and minimize that current because it's in a portable setting. So I'm going to use a VCC of 12 volts from the battery and then try and minimize the current through those two devices. Now from a linearity point of view, that may not be the best choice, but hey, that's what I'm going to go and we'll stick with that. Again, this is just a video log of what I've done, and the approach that I take, right or wrong, seems to work for me. So that's what I'm going to stick with. So just running through what I did for the numbers, I'll start off with the second stage, what I call stage 2, and then we'll move on to stage 1. So what we have here, for a Class A amplifier, we know that the power that this thing could potentially generate is VCC minus the voltage at the emitter, because I'm not fully bypassed here, squared, divided by 8 times our load resistance. So if I want to generate half a watt, I can rearrange this formula to determine what our load resistance needs to be. So I can plug it in. Standard for me, I'm just going to make the emitter voltages 10th of VCC. So in this particular case, it'll be 1.2 volts. So 12 minus 1.2, all squared, divided by 8 times half a watt, comes out at 29 ohms. So I want to present 29 ohms here as a load resistance for this particular transistor here. With a 50 ohm load, we can then work out what the turns ratio needs to be for that output transformer, or T3. So N equals square root 50 over 29, or comes out at 1.31. So we'll use a turns ratio of 7 turns to 9 turns will be the transformer. So we'll have 9 on the second and 7 on the primary. Just doing a quick double check to make sure we've got the right inductance being presented for that 50 ohm load. It needs to be roughly at sort of 4 to 5 times 50. With an FT37-43 I should say, 9 turns comes out at 28.35 microhenries, and we know that inductive reactance is XL equals 2 pi FL, so we can plug in 14 megs and our inductance and we come out with 2497, so again 2494 ohms, which is well in excess of 5 times 50, so no problems there. So having determined that, just need to work out now what the current, the quiescent current is through this particular device. So we know with a Class A amplifier, the maximum or the best efficiency we're going to get out of this thing is no more than 50%. So if we use that assumption then, if I'm going to generate half a watt as an output, then I'm going to consume in the device itself, or dissipate within the device itself, half a watt, which means I need to poke into the whole amplifier itself from a power point of view, 1 watt. And we know that power equals volts times current, so we can work out then what our current needs to be into this whole amplifier, or the stage 2 that is, to be able to generate half a watt out. So 1 watt divided by 12 volts minus 1.2, so our VCC minus our emitter resistor, or emitter voltage, gives us the voltage across that device, comes out at 92 milliamps. I'm going to add, say, a good 25% of that, not too high because it's a portable rig, but not too low, so let's just sort of round that up to 120 milliamps. So here's 120 milliamps as our quiescent current through this device. So now we've got that set, then it's just a matter of working out what our biasing resistors need to be in order to establish that. So I said before that I'm going to set for both the stages an emitter resistance, say again an emitter voltage of 10% of VCC, so 1.2 volts. So 1.2 divided by 120 milliamps comes out at 10 ohms, which is a standard value, so that's good straight away. And it's going to double check because on stage 2 we've got a reasonably high quiescent current going through that. Just want to make sure I'm not going to exceed the power dissipation for these quarter watt resistors. We know that power equals I squared R, so 120 milliamps squared times 10 ohms comes out 144 milliwatts. So that's just under, well, roughly half of what the resistor can dissipate, so we'll leave it at that. So that's good. Right, so just moving on to the next stage, and what I might do is just try and leave that circuit displayed up top. We can go backwards and forwards. Right, so now just working out what R22 is, so the second stage and the second resistor of the voltage divider's biasing. We said before that the range of beta for that particular device is between 50 and 200, so we'll take the geometric mean and come out at 111, so we'll use that for our biasing calcs. Noting too that our base current is our collector current divided by beta, and as a rule of thumb our emitter current is essentially the same as our collector current. The only difference between the two is the base current, which is very small. So that's an assumption. That's again an approximation which works just fine. So plugging that in, so the voltage across R22 is the voltage at the base. So 1.2 volts, our emitter voltage, plus 0.7 for that forward biased junction, divided by, in order to get a nice stiff voltage divider current, 10 times the base current, so 120 milliamps. Because of this we can plug it into here, divided by 111, our beta, comes out at 175 ohms, so we'll use 180 ohms as a near standard value. The second resistor in that voltage divider biasing, this one here, just there, its voltage across that is going to be 12 volts minus the voltage at the base, and we'll divide that by 11 times the base current. Why 11? Because we've got now that base current coming out of the transistor being added to what was 10 times through here, which gives us 11 times the current through that second resistor. Work that out, comes out at 849 ohms, so we'll just round that down to 820 as the nearest standard value. So So that establishes the DC biasing point. And what I want to do now is, you'll see here in the emitter circuit, I've got a DC blocking capacitor, as not to interfere with the DC biasing, and another resistor here, same on the stage 1, which we'll get to in a sec. So I've got that second resistor in parallel with, from an AC point of view. Why AC? Because then that capacitor there becomes a short. So from an AC point of view, these two are in parallel, and then using the gain calculation, I can work out what that needs to be in order to get the right gain for that particular stage. So that's what we're doing just here. So gain should be 10 log our load resistance divided by the effective emitter resistance here, what I'm just going to notionally called RE dash, where RE dash is the combination of the two sides of that circuit down here. Now, for this second stage, I was going to try and aim for around 10 dB, and we know that from our earlier calculations that the load resistor is going to be 29 ohms, or the load resistance is going to be 29 ohms. So I can now rearrange this formula here to make RE the subject and then solve for it. So 29 divided by 10 raised to 10 dB divided by 10 comes out at 2.9 ohms. So this combination needs to equal 2.9 ohms. Resistors in parallel, that's the formula here rearranged. So now we can say that 2.9 ohms equals 10 ohms in parallel with what's called X ohms. So therefore X equals 1 over 2.9 minus 10 comes out at 4.08 ohms. So I'll use a standard value of 3.9 ohms. So that value there is going to be 3.9 ohms. And that's pretty well all of the components for the first stage. So now we'll go and work out what we need for stage 1. And it's going to be very much exactly the same process. We'll work out what that turns ratio needs to be, we'll work out what the current through the device needs to be, work out the DC biasing, and then work out what that resistor there needs to be in order to get the right kind of gain. And then later on we'll finish off by working out what T1 needs to be. So moving on to stage 1. So again we need to, from a biasing or from a matching point of view, we need to find out what the resistance or the impedances, or I'll use the resistance, looking into here, and then that needs to be matched through to whatever this device here needs to be in order to generate sufficient power to drive this side. So looking in here, it's going to be approximated, noting that our VCC rail here from an AC point of view is effectively at earth because it's been heavily decoupled there. So because that's effectively a short circuit at AC, you can imagine then that this whole line here folds over to earth, so a whole lot of things are in parallel. So again, looking in here, we're going to have R22 in parallel with this folded over, R21 in parallel with this folded over, a high impedance here plus our load resistance here. Now that high impedance is such that I can ignore the circuit here, or that portion of it. It'll have minimal effect on what the overall looking in there, so I can ignore that. And then looking into the transistor here, it's going to be little Re plus whatever our effective resistance is here. Right, so having just said all of that, that's effectively what I've got written down here. So R2, second stage input, is R21 in parallel with R22 in parallel with beta AC. Now it's AC, not DC. Multiplying little Re plus our 2.9 ohms, in other words, what that effective resistance is there. Now beta AC is our transition frequency divided by our frequency of operation, so 100 megs divided by 14 megs comes out at 7.14. So now we can start to plug things in. So 820 ohms in parallel with 180, 7.14 times 26 millivolts divided by our emitter current in milliamps. So in that case it's just 120 plus our 2.9 comes out at 18 ohms. So now we know what the second part of that transformer needs to be matching. Right, so getting back to then what the primary of that transformer needs to be, this is for T2. We know that in order to generate half a watt at the output of stage 2, we need to be feeding it, if it's going to generate roughly 10 dB gain, 50 milliwatts. So again, we can use exactly the same formula as I used in stage 2, which is that one there, to solve for what the resistance needs to be, what's being seen at the collector of that stage 1. Right, so so that's exactly what we got here. Again, rearranging that formula to make our RL the subject, and then plugging in the various values, we come out at 292 ohms. So from a turns ratio point of view, we need to match 292 ohms to 18 ohms. So what we worked out before is the input resistance to stage 2 comes out of turns ratio of 4.02. So I'm going to use 3 to 12. It's close enough for that. Right, and exactly the same in terms of working out what the current through that device needs to be. Same thing as before. It's a Class A amplifier, so we're going to consume or dissipate within the device itself 50 milliwatts. We're going to try and output 50 milliwatts into stage 2, so therefore we need to have an input power of 100 milliwatts. Again, power equals volts times current. We can work out what the voltage is across the device, what power it needs to be total. Comes out at 9.2 milliamps. Again, gives a little bit of a head factor. I'm going to round that up to 12 milliamps. Could be a whole lot higher than that for some better linearity with the device, but I want to try and minimize the current draw, so I'll give 12 milliamps a go and see how we work out. Right, so stage 1 emitter resistor, exactly as we saw for stage 2. 1.2 volts is the voltage at the emitter. 1.2 volts divided by 12 milliamps comes out 100 ohms, which is good, and the power dissipation for that is fine too. Right, so R12, so this is first stage, the second resistor in the voltage divider biasing, as exactly what we saw in the first stage, so I won't go into that. Again, the voltage at the base divided by 10 times the base current, and we'll use a standard value of 1800 ohms. The other transistor, so again, the other resistor in that voltage divider biasing, again the voltage across it, so the base, that's the base voltage there, divided by 11 times the current. We'll use a standard value of 8200 ohms. Right, so there goes the 3 resistors that set up the DC biasing for that particular transistor. Now, again, as we saw in the first one, need to work out what that resistor there is in order to present from an AC point of view our gain, or the right value of emitter resistance, or RE dash here. 10 log RL over RE dash. Ideally want to get somewhere around 20 dB for this particular device, and acknowledging that our RL, as we worked out before, is roughly 292 ohms. So having said that, we can rearrange the formula and make RE dash our subject, and that comes out at 2.92 ohms. So therefore 2.92 ohms is the overall parallel resistance here, made up of 100 ohms and this X, noting that at 14 megahertz this is around 0.1 ohms if I recall, which is effectively 0, so we'll just make that 0 and just work out what X is. Again, exactly the same formula as we saw for stage 2. Solving that, we come out an X of 3 ohms. So I could go down to 2.7, or I could go up to 3.3. I'll go slightly higher, so we'll run with 3.3 ohms. Right, so that's it then. So now we're solved for that resistor, 3.3 ohms. So the only thing now left for this particular circuit is to try and work out what that input transformer is there. So I've got 50 ohms here, matching through to whatever the input resistance is looking into this device. So same approach that we use for stage 2. It's going to be R11, so that's the first resistor in the voltage divider biasing, in parallel with the second, beta AC, little re plus 2.92 ohms, which should be worked out up here. Again, plugging in our values, solving for it, same beta AC, it's the same device, therefore the same FT, comes out at 20.57 ohms. So N then, so matching 50 ohms to round it up to 20.6, comes out at 1.56, so we'll use a ratio or a turns ratio for that transformer of 7 turns to 11 turns. So it'll be 11 turns on the primary and 7 turns on the secondary to match that 50 ohms to roughly 20.6. And that effectively is all I did in terms of the calculations. And then if I was just to zoom up on this, that's effectively exactly what we see there. So I'm not quite sure if I can keep in focus there. I think that's pretty well in focus. So we've got the two stages there. That's our T1 coupling in. We can see that the capacitor on the DC blocking capacitor for the emitter resistor, so the two resistors there, that's the normal emitter resistor, and that's that little small one in parallel. Exactly the same approach for stage 2. Coupling transformer between stage 1 and stage 2. Only 12 milliamps flowing through here. That's pretty well stone cold. And then through this second stage here is 120 milliamps. But like I say, you can run that pretty well constant, and it's not a problem at all. Using 26 gauge, let me just double check there, I'm pretty sure it's 26. Yeah. Using 26 gauge for both the transformers here. I probably would have got away with, again, 26 gauge on T3. The only reason why I've got a slightly heavier gauge there is I just opened up the junk box to get an existing transformer and just removed a couple of windings to get down to what I wanted to, so just being a little bit lazy there. But again, to be on the safe side, that's fine for that 120 milliamps. And then just a little, not quite in view there, little 50 ohm dummy load. Right, so in terms of how it works out, I'm pretty happy with what I've got at the moment, so I don't think I can get both in view there, so we'll just leave it out. So just arcing it up, that's currently sitting on 14 megs. Just to zoom that out a little bit, excuse the creaky camera. So that's currently sitting on 14 megs, and if we just drop that down now down to 3, so as expected, getting some reduction in gain, not unsurprising given that there's no other negative feedback to try and squash down the gain in order to get a wider bandwidth. But again, I wanted to run this notionally at 14 megahertz for this 20 meter rig, so that's fine. The overall voltage gain on that is working out to be, well, the gain I should say, around 26 dB total. So I think that's fine. I'm not going to grumble too much about that. So I think we'll just leave it as it is and go from there. The only other thing too, 14 megs. If we go down to 5 volts, then we're starting to get a bit of compression there, but that's running there on 510 14, so that's the equivalent of 500 milliwatts or half a watt to that 50 ohm load. So that's good. So that's can obviously generate what I want into that load there. That's stone cold, and like I say, it's barely warm. So I think that sized heatsink will be just fine for that particular device there. In fact, I'll probably get away with something as small as that, I think. But we'll leave that as it is. Okay, well, I'm going to say 73s there. Like I say, this was just a video log. It is not a tutorial. It's just the approach I took. No doubt there's errors in those calculations, but yeah, I'll keep learning and keep reading and see what else I can pick up. But like I say, this seems to work for me. The only thing I might actually say from a construction point of view, let me just turn that off so I don't short anything. I totally acknowledge that this, what's the best angle for light there? Let's go with that. I totally acknowledge that this strip board here is not the best board for RF circuits. I have quite good success with it, and as you can see there, hands around and up and down with the voltages and the frequency, it's nice and stable. Certainly I haven't seen any instability with this from my playing around. But what I do tend to do is cut tracks. So there's a couple of tracks been cut there. Underneath these transformers I've decided to cut 3x3. Again, there's a track cut there. You can't quite see very well, but I'll just describe it. On the emitter, I've cut the track right next door to it, and then as close as I can to the last resistor, I've cut the track again. And what I'm trying to do there is I'm trying to crudely separate the gazintas from the gazoutas. So I'm trying to present or protect or separate the input from the output. So the input being, for example, the base circuit. So I'm trying to minimize that high voltage that's coming across on the collector from feeding back into the base circuit. So I try and cut the collector track as close as I can to the collector in order to minimize that voltage there feeding its way back through capacitive coupling between those two tracks back onto the base track. And my experiences to date, if you do that, then at the frequencies I'm using, and I've totally acknowledged that sort of 80 through 20 meters, I've had no problems with this particular board. I think if you were to leave those tracks uncut and big long parallel tracks between outputs and inputs, I think you'd start to ask for trouble in terms of coupling between, or the capacitive coupling between those tracks. So anyway, that's just what I've done there, and it's a bit hard to see unfortunately, but there's tracks all over the place cut, and that's just a matter of using, I'll just reach up here, just a drill. So if you just, I've got a piece of masking tape on the end to protect it, and if you're just to push it onto a little hole there, a little bit of pressure and to twist, and you very easily and quickly cut away the copper and create a cut. Just be careful that you get the swarf off, because obviously you're now producing copper swarf, which could potentially cause short circuits. Anyway, that's all I wanted to say there. The only thing of interest, I think I mentioned it before, my favourite orientation, or the method I use for the strip board, is the bottom one is ground. The next row up will be the emitter row, then the base row, then the collector row, then the VCC row, and then earth again. So it makes it nice and easy then for decoupling the VCC rail, just to have an earth right next to it. And then at the end of each end is a little tack made out of desoldering wick, one on each end of the ground rails, and that seems to work quite well. That provides obviously the mechanical bonding, or mechanically holds the board, to the ground copper board, as well as providing that ground plane up to the DC rail. So anyway, that's my favoured configuration, and that seems to work quite well. Okay, I have rambled on for way longer than I wanted to. That may or may not be of interest, but like I say, that's just a log of the approach I've taken with this particular amplifier, and pretty happy with that. And I think now it'll be a matter of just continuing on and just making the circuit up. Just sort of, I've got some other things I'm doing in parallel, and I'll just keep working on this 20 meter portable rig. Anyway, 73s, and we'll catch you next time.